Hi guys, we're picking up in chapter 16. I'm in the second PowerPoint. I'm on slide 8. This section has a lot of just working problems, so I want to put it on the chalkboard and kind of work through it with you. In the previous video, I hope that when I'm showing the PowerPoint and it clicks through all the different steps of the answers, you guys need to be working those on your own on paper. Try to work ahead of me if you can, and then double check what you're doing with what I do on the board. So we're starting finding the pH of bases. So when we have a base, the two kinds of bases. If we have a strong base, that's going to be the ones that completely ionize. The concentration of the base will typically be equal to the concentration of the hydroxide ions in solution. If we have a weak base, then we're going to have to set up an ice table. And if you look at slide number 8, it shows you kind of a generic reaction for any weak base. You put a base in water, it's going to react to form a hydroxide and the conjugate acid of the base that you started with. It also shows the equilibrium expression where we can hopefully plug everything in, solve for the hydroxide concentration, and then from there get to our pH that we're usually looking for. Okay, so let's work some problems. So I'm going to skip to slide 9. If I want to find the pH of a solution that is 0.1 molar in sodium hydroxide, again, if you look back at HCl, I did, and this is a few slides ago, I did an ice table for HCl where I showed that the initial value of HCl, it all goes away, so I end up with 0 for equilibrium HCl, but then the hydrogen concentration was 0, and then I added the total concentration of HCl, which was, I think it was 0.1. So basically the initial HCl became the H plus concentration. Sodium hydroxide is going to work the same way. If I have 0.1 molar sodium hydroxide, when you put it in solution, it's going to convert into sodium ions and hydroxide ions. So essentially what I know is that my hydroxide concentration is going to end up being 0.1 molar also. The concentration of the strong base equals the concentration of the hydroxide. Now, if I do the negative log of the hydroxide concentration, that's going to give me the POH. So if I do negative log of 0.1, the pH is going to end up being, or excuse me, the POH is going to end up being 1.0. And then if I do 14 minus that, the pH will equal 13.0. And it should make sense that if I have a strong base, that should give me a high pH, which 13.0, that's a very basic solution. Okay, so that's the problem on slide 9. Now if I go to slide 10, we're going to have similar setup. I'm going to have 0.1 molar, but this time it's a weak base. Ammonia is a weak base. When it is put in water, it will partially react with water and form some hydroxides, but it will not end up being 0.1 molar. It'll be some value less than that. I don't know what it is, so we're going to have to set up an ice table and work through the ice table to figure this out. Okay? So step 1, I need to be able to write a reaction. Okay, so that's my concentration. When I put my ammonia in water, in order to form a hydroxide, ammonia can't do it by itself. What happens is the ammonia reacts with water. It essentially takes a hydrogen from the water molecule to make NH4 plus, and then the water molecule, once it's lost a hydrogen, which it loses the H plus, that leaves a hydroxide behind. So that's my reaction that's going to happen when ammonia is put in water. That's a weak base reaction. Set up my ice table. My initial concentration of ammonia is 0.1 molar. My initial ammonium concentration is 0. My initial hydroxide concentration is 0. Now again, in water there is a little bit of hydroxide present in the solution, It's actually 1 times 10 to the minus 7 molar. We established that in the first part of the PowerPoint. But typically that value is small enough, the 1 times 10 to the minus 7, that's a small enough value that it, in comparison to the hydroxide that we're about to make, it should be orders of magnitude greater in most cases. And because of that, the amount that I started with, if it's tiny and I'm making a lot more, we can ignore that initial amount. Okay? So most of the time that's going to work out for us. Alright? So, I've got numbers for everything except water. Well, remember, water is the solvent in an equilibrium expression. A liquid does not appear because its concentration remains constant, so it gets lumped in with K. So essentially, I'm just going to put a line through it, and I'm going to ignore the column for water because it's not going to affect the mathematical setup that I'm going to have. So, my ammonia, a little bit of it reacts. I'm going to call that minus X because the concentration of ammonia is going to go down by that much. It's a 1 to 1 to 1 reaction, so it's going to be plus X under ammonium and plus X under hydroxide. So my ammonia concentration ends up being 0.1 minus X, ammonium is X, and hydroxide is X. At that point, I can take those things, my equilibrium concentrations, plug them into the equilibrium expression. Kb for this base equals X times X on top, so that's going to be X squared. On the bottom, it'll be 0.1 minus X. Now, to solve this problem, I need, and the question I asked initially was to find the pH of the solution. So my pH is the unknown. That means that I have to have all the other numbers that I need. So to solve this, I need to know what the Kb value is for this base. It was not given in the problem. It's not on the slide. So you have to know that when you work one of these problems, if you need a Ka for an acid or a Kb for a base, you have to look that value up. Okay, it's in Appendix D of your textbook. So you look at that. Coincidentally, we did a problem earlier with acetic acid. The Ka of acetic acid is 1.8 times 10 to the minus 5. The Kb for ammonia is the same number. It is purely a coincidence. There's no relationship between those two, the acetic acid, and the base ammonia. It's just a coincidence that they're the same. So Kb is 1.8 times 10 to the minus 5. So I'm going to write that in. Excuse me. Now, at this point, if I compare, at this point, if I solve it properly, I'm going to have to do the, excuse me, I would have to do the quadratic equation to get X. If I want to avoid that, I have to assess whether is the amount that I'm losing of the base going to be a significant amount or not. I compare the initial concentration of the base, 0.1, to the Kb value. And remember, the Kb value is a representation of how strong an acid or base is, which tells me how much of it dissociates. If the initial concentration is at least 1,000 times bigger than the Kb value, then that means that the amount that's going to dissociate will be insignificant. So, 0.1 divided by 1.8 times 10 to the minus 5, that is a significant difference of greater than 1,000. So that means I can ignore the minus X, which is going to allow me to simplify to X squared over 0.1. At that point, I can multiply the 0.1 over and then take the square root. So X will equal, I'm going to plug it in my calculator, calculator, there it is. and I got 0.00134. Now that's the molarity of X is my hydroxide concentration. So if I do the negative log of that, it's going to give me the POH, and then 14 minus that value would be the pH. So negative log. Well, this calculator doesn't have a negative log value on it. So, I'm just going to trust you guys to finish it. I may stick that value into the slide, but a negative log of this number is the POH, 14 minus that gives it the pH. If I remember right, I think it might be 2.87 is my POH, and then 11.13 is the pH value. Okay, so I'm going to move on from that. So now the next slide, there are going to be times when we are dealing with acids and bases where you're going to have an acid, let's say acetic acid, CH3COOH, and then we can look up the Ka value for that. Ka for acetic acid is 1.8 times 10 to the minus 5. But there are going to be times that when we are working a problem, instead of having acetic acid in our problem, we may be dealing with its conjugate, which is acetate. So acetate, CH3COO minus, if that's what's present in the solution, this is the conjugate base of acetic acid. Acetic acid has a Ka value that represents how strong of an acid it is. Acetate would have a Kb value that represents how strong of a base it is. The way I find, if I know one of the values and I want the other one, there is an equation that you need to know. Kw, which is 1 times 10 to the minus 14, equals the Ka of an acid times the Kb of the base. Now the way this is derived is actually shown on slide 11 of the PowerPoint. It shows the step-by-step way that you combine the Ka for a reaction and the Kb of a reaction, combine those together by Hess's law, and you end up doing Ka times Kb to equal Kw. Okay? So it could be derived, but if we just learn this equation, it's going to allow us, if we have the Ka of acetic acid, we can easily calculate the Kb for acetate when we need it. Now this is important that if you look in the appendix and you only find a weak acid or weak base in the appendix, but for a given problem you need its conjugates, Ka or Kb. If it's not in the table, we can still find it through a simple one-step calculation. Okay, so if I plug in the Ka for acetic acid, plug it into this equation, I know Kw, I know Ka. If I divide that over, I can solve for Kb. And if you do that, the Kb value for acetate, 1 times 10 to the minus 14 divided by 1.8 times 10 to the minus 5, will give you 5.56 times 10 to the minus 10. So now we know how to get both K values for a conjugate acid-base pair. If you know one of them, it's easy to find the other one. All right? Now next slide. So slide 12, again, demonstrates this equation, and it shows a number of acid-base pairs. And what you notice is on the left side of the image are the acids, and as you go up, the Ka values are becoming stronger. And then on the right side of the picture, the conjugate base, as the Ka values get bigger, if you look at the Kb value, as Ka gets bigger going up, the Kbs are getting smaller. And then as we go down, the Kas are shrinking, but the Kbs are getting larger. So it shows the inverse relationship between Ka and Kb. It's demonstrated by the fact that if these two numbers have to multiply to equal a constant, if one of them goes up, the other one has to go down because the product of the two numbers has to stay the same. Okay? All right, so moving forward. The next topic, this is a challenging topic for a lot of people. How can I find the pH when I have a salt in solution? So we know how to do a strong acid and a weak acid. We know how to do a strong base and a weak base. But another type of compound that we can dissolve into water is going to be a salt. So let's start with the most common salt of all. What if I have a 0.1 molar NaCl solution, sodium chloride? What will the pH of that solution be? So what I have to think about is when I dissolve sodium chloride in water, we know that ionic compounds that are soluble, when they dissolve, they split apart. Remember, they're strong electrolytes. So when they split apart, really what I'm going to have in that solution is not NaCl. It's going to be 0.1 molar Na plus, and it's going to be 0.1 molar Cl minus. So I'm going to have these two ions floating around independently of each other. They really don't have anything to do with each other once they're in the solution. So I need to think about, will either one of these ions either behave as an acid or behave as a base? Will either one of them have any acidic or basic properties? Okay, so we have to think about each one separately. So let's think about sodium first. The sodium cation. Is it an acid or a base? Well, honestly, when I look at that, it's kind of hard to tell on its own what it's going to do. But I have to think about, are there any acids or bases that I know that are related to this? And the answer is the sodium ion. I know that if I had sodium hydroxide, which is a base, when it gives up a hydroxide, I'm left with the sodium cation. So this is the conjugate acid of sodium hydroxide. So I'm going to write in parentheses NaOH, and that in this solution I don't actually have any sodium hydroxide present. But I'm thinking about sodium hydroxide, saying I know that this is a strong base, it's an extremely strong base, and the strength of its conjugate will be inversely proportional. So if this is a really, really strong base, that tells me that the sodium cation is going to be a really, really weak conjugate acid. In fact, it's so weak that it isn't going to do anything significant in the solution at all. It's just going to be a spectator ion. It's not going to cause any new H pluses or OH minuses to be formed. So I'm just going to ignore it. It's a extremely weak conjugate acid that's so weak it won't affect the pH. Once I make that decision, I no longer have to pay any attention to it. So then I look at the other ion, Cl minus, and I have to think what acid or base is related to Cl minus, and we should know that hydrochloric acid, HCl, is the acid that chloride comes from. So sometimes I'll refer to these as the parent acid and the parent base of my ions. HCl is the parent acid. It's a strong acid, so the conjugate base that comes from it will be extremely weak. So weak that I can ignore it. If I'm ignoring both of these ions in solution, then what I'm saying is neither ion is going to affect the pH of the solution at all, and therefore the pH of the solution is going to be the same as it was for water. This solution will have a pH of 7.0. It will not be acidic or basic. It'll look just like water. Okay? So let's try another one. What if I had 0.1 molar ammonium chloride? Okay, so again, you have to recognize I have a cation and an anion. Now, the cation can't be H+. If the cation is H+, then the compound is an acid. If the anion is OH-, then the compound is a base. So I have a cation and anion that are not H plus and OH minus. So this is a salt. When a salt's in solution, it splits. I look at each ion separately. So I'm going to have NH4 plus, and I'm going to have Cl minus. Cl minus we've already looked at a minute ago. Its parent is HCl, strong acid, extremely weak conjugate. I'm going to ignore it. Cl minus is not going to affect the pH. But ammonium is related to ammonia. Hopefully we know ammonia is a weak base, and its conjugate is going to be a strong enough conjugate acid to affect the pH. Now I have to be careful. We call strong acids like HCl and HBr and HI, those are the ones that completely dissociate. That's not what we're saying here. This is a weak base. Its conjugate will be relatively strong, meaning it's strong enough to affect the pH. So this ion is going to affect the pH. I know that its concentration is going to be 0.1 molar, so then I have to set up an ice table and figure out what the pH is going to be. Okay? But I know initially, and there's two ways this question can be asked. I could ask a qualitative question and just ask a 0.1 molar ammonium chloride solution, would it be acidic, basic, or neutral? Okay? Knowing that this is, like, ammonia is a base, ammonium is a conjugate acid, and it's going to affect the pH, I know that this solution is going to end up being acidic. The pH will be below 7. The problem we did a couple minutes ago, sodium chloride, we said that salt, neither ion is going to affect the pH at all, so that solution will be neutral. And then if we have a salt where we're worried about the conjugate base, then that would give us a solution as a pH above 7, which is basic. Okay? So we can just qualitatively assess that pretty easily by looking at our parent acid and base and then deciding on the strength of our ions. Okay? Now, what if we actually want to calculate it? Well, that's going to be a longer process, but I know once I've decided which ion to look at, then I have to write an ice table, write a reaction, and set up an ice table for that ion. So ammonium ion in water, again, you can show the water or not, but the ammonium gives a hydrogen to the water, make NH3 plus H3O plus. Ice table, starting with 0.1 molar ammonium. Again, keep in mind the chloride we decided is a spectator. Once we decide that, we don't need to see it anywhere in the reaction. It's not part of this process. The chloride ions are just floating around, not doing anything. Okay? I ignore the water column. The ammonia starts out at 0. The hydronium starts out at 0. Minus X, plus X, plus X. I get X, 0.1 minus X. At that point, I can set up my expression. For ammonium, I'm going to have a Ka value equals X squared over 0.1 minus X. Having that, I do need to know for this reaction what's my K value. Well, again, we know that the Kb for ammonia is 1.8 times 10 to the minus 5. If I do Kw over Kb, that'll give me the Ka for ammonium. So 1 times 10 to the minus 14 divided by 1.8 times 10 to the minus 5, that's the Kb for ammonia. That'll give me the Ka for ammonium. If you do that, the Ka value is going to be 5.6 times 10 to the minus 10. Once I know that, my initial concentration is a large number of more orders of magnitude greater than my KB value or Ka value. So I can drop the minus x. So at that point, it's going to be x squared over 0.1. So now I can solve for x. Let's see, 5.6 times 10 to the minus 10 times 0.1. Oh, I messed that up. And then take the square root. So I got the x equals 7.48 times 10 to the minus 6. That's my hydroxide. Notice that's my hydronium concentration. Take the negative log of that. Again, this calculator doesn't have a log button on it, so take the negative log, that'll be my pH. The negative log of that number. Okay? Again, if I add this to a slide, I'll put it into the PowerPoint when I get a chance to. All right, that's a good place to cut off the video. We'll pick it up on the next slide.